Okay, so there's going to be a couple examples here that are wonderful examples, just like what we did in the lines and functions review. One of the things we reviewed in the lines and functions review was how to get common denominators, and another one was how to multiply by a conjugate. And these two problems are going to use both of those techniques. I can guarantee you at least one of the next two examples, one if not both, will be on your first exam and will also be on your final exam. These two are huge. You need to know how to do these, and you need to know how to do these by hand. So please, please, please take extra special notice of how to do these problems. They are on the exams. So the first one says, find the derivative of y with respect to t, so we're no longer using x's, and that's fine, for the function y equals 4 over t using the definition of derivative. Okay. So what's the definition of derivative? Well, now instead of finding f prime of x, we're actually finding f prime of t. T's our variable. So it'd be the limit is h approaches 0 of f of t plus h minus f of t all over h. That's the definition of a derivative right there. And anytime it says using the definition, you have to do this limit process. Again, on the notes, I do it in the 4 or 5 separate steps, but here I'm going to do it all at once for you. So this is the limit as h approaches 0 of f of t plus h. So go back to your original function. Wherever you see a t, you're going to be plugging in a t plus h. So this would be 4 over, instead of just t, it's now t plus h. Minus, let me use some colors again here. I don't want you to get lost. This is the red part that I just did, okay? Minus f of t, here's the blue part, so that would be minus, well, the original function, using blue, the original function is simply 4 over t, and then this is all over h. Well, if you go back to the lines, this one was in the algebra review, this is called a compound fraction, and with a compound fraction, when you have fractions over fractions, one of the techniques is to get a common denominator, of the numerator and treat the numerator, so we need to get a common denominator and combine the numerator to a single term. So what do I need to do to get a common denominator? I need to multiply by whatever it's missing. So the second one is missing the denominator from the first one, which is t plus h. So I'm going to multiply it times t plus h over t plus h. And this first one's missing the second denominator, which is simply t. So I'll multiply the numerator and denominator by t over t. Okay. So let's have the limit as h approaches 0. I'm trying to get a common denominator. Let's clean this up. T times 4 would be 4t. And then on bottom I have t times t plus h. Leave that in factored form. Minus. And on the top of the next one, I'm going to distribute that 4 through to both of those. I would have a 4t plus 4h. Be sure you distribute that 4. And on bottom I have a t and a t plus h. All of this over h. Okay. Now I have a common denominator, and because I have a common denominator, I'm actually able to combine these. I do want to note, though, remember when you subtract, you have to distribute that negative to both of those terms. It's called distributing the negative, so you've got to be really careful here. So I have a 4t, and then I'm going to have, well, all of this is over the common denominator, which is t and t plus h, right? I'm going to have that, when I distribute the negative, a minus 4t, and then I'm going to have a minus 4h. Be extremely careful with distributing that negative. I'll put a little star right there. You've got to remember to distribute that negative to that second term. So when I do that, I notice, all of this is over h. I can't forget that. I notice that those 4t's cancel. So this is the limit as h approaches 0 of negative 4h all over t times t plus h all over h. So now I have a fraction over a fraction, but it's not quite a fraction. Well, I can make it a fraction, though. Can I write h as h over 1? And now you got to remember, how do I handle when I have a fraction over a fraction? And this is when you multiply by the reciprocal. This was the saying keep, change, flip. So what you're going to do is you're going to flip that bottom fraction and change it to multiplication. So this is the exact same thing as, the limit as h approaches 0 of, well, it'll be negative 4h all over t times t plus h in parentheses. But then I'm going to take h over 1 and I'm going to flip it. So that's going to become 1 over h. changes to multiplication, but now notice, sweet, those h's are going to simplify. So I'm left with the limit as h approaches 0 of, well, on top I would have a negative, seems like I'd have a negative 4, right? And on bottom I'd have a t times a t plus h. Well, this is something that I can use the limit. I could take h and I can plug in 0, and this would be negative 4 over t times t plus 0, which is negative 4 over t squared, our answer. Negative 4 over t squared, which would be our answer. Okay? So, doing it all at once. I am able to do it all at once. I can separate it into the individual parts. If you want to see it separated into the individual parts, please check the solutions. In this video, I went ahead and did it all at once. What was the key here? Get a common denominator, combine like terms, keep, change, flip, that invert and multiply, right? H is h over 1, keep, change, flip, right? Simplify, then evaluate your limit. But I guess one question might have been, why the heck did I do all of this to begin with? Well, what I want you to do is I want you to go back to the beginning. Could have you evaluated that limit at the beginning? So if we wanted to evaluate that limit, we would plug in h equals 0 into that original step. But look what happens if we do. If we plugged in h equals 0, we'd have 4 over t minus 4 over t. That would give us a 0 on top, and we'd have a 0 on bottom, which is our indeterminate form. So we had to simplify. We had to do this because we would have gotten 0 over 0, saying the limit is undefined. This was absolutely necessary. All of this work was absolutely necessary, and we couldn't have actually plugged in the 0 until the very end when we did. So all of that work was necessary. Might suck, but that's calculus. Lots and lots of work to get a very simple answer. Let's look at this next one. Another one of my favorite examples, and again, one or both of these examples will be on the test, something very similar to it. The next one says, determine d dx of square root of x. So what's that d dx mean? Again, that means the derivative, and we want to use the definition of the derivative. We are back to x's on this one, great. So we know that f prime of x, or the derivative, is equal to the limit as h approaches 0 of f of x plus h minus f of x all over h. And I want you to write that on your paper every single time until you memorize it. You should even write it on your paper on the test when you're doing these problems. That's the goal of the problem. So let's give this one a try. Let's come in here. The limit is h approaches 0 of f of x plus h minus f of x all over h. So what is f of x plus h? Again, let me use some colors to kind of help you show you what I'm doing and where I'm going with this thing. So what's f of x plus h? Well, we have the limit as h approaches 0 of f of x plus h would be the square root of, instead of x, we'd have our x plus h in there, right? So there's the red one. Minus, now let's do the blue one. The blue one's just the original function, so that's the square root of x, all over h. So there's my function right there. F of x plus h is the square root of x plus h. F of x is just the square root of x. Well, notice what happens. There's the definition of the derivative. We found the derivative, but let's see if we can do it. If we wanted to plug in the limit as h approaches 0, what happens if we plug in 0 for h? Well, 0 for h, this would be the square root of x minus the square root of x, so we get a 0 on top. H, we get a 0 on bottom, so we'd have a 0 over a 0, which is that indeterminate form, undefined, doesn't work. So this means we had to do one of the tricks. Well, one of the tricks is what we learned in the previous section. One of the tricks is when we did the limit section and we were trying to evaluate this, we had to multiply it by a conjugate. So we saw it in a previous section where we did it for evaluating, where we evaluated limits. We also saw it in the algebra review packet. So we've done this a few times. It's called rationalizing the numerator, multiplying by the conjugate. We have to get rid of the radical in the numerator. And to do that, you multiply it by the exact same thing, the square root of x plus h, and the square root of x, except you change the sign. So instead of subtraction, it would change to addition. Square root of x plus h plus the square root of x. Okay, this is called rationalizing the numerator when we multiply by the conjugate. And the idea here is you distribute the numerator, but do not, absolutely do not distribute the denominator. So we'd end up with the limit as h approaches 0, and let's distribute that numerator. So we'd have the square root of x times the square root of, the square root of x plus h times the square root of x plus h. Well, that's the square root of x plus h squared. Our outer terms would be plus root x times square root of x plus h. Our inners would be square root of x times minus square root of x times square root of x plus h. And then our last would be minus the square root of x squared. On the bottom, again, do not distribute the bottom. We'd have h times the quantity, the square root of x plus h, plus the square root of x. Let's go for this. Notice, why did we multiply times the conjugate? Well, those middle two terms on top are going to cancel, the plus root x plus h, and the minus root x plus h. The first term, square root of x plus h quantity squared, is x plus h. And the last term, the square root of x squared, is just an x. So let's put this together. Now we have the limit as h approaches 0 of x plus h, middle terms are gone, then we have that minus x all over h times the square root of x plus h plus the square root of x. This is looking really nice. I want you to be very careful. We have to do this in multiple steps. You might see that the x's cancel and the h's simplify, but that is two steps mathematically, two separate steps. We have to cancel the x's first because of order of operations. The limit as h approaches 0 of h over h times the square root of x plus h plus the square root of x. Now my h's can simplify. I cannot do those two steps in one. Those are mathematically two separate steps. So this is the limit as h approaches 0 of 1 over the square root of x plus h plus the square root of x. Now that we've rationalized the numerator, we can evaluate that limit. So to find the limit as h approaches 0, we just plug in a 0 for h. Notice I don't have to write that limit as h approaches 0 anymore, and I'd have the square root of x plus the square root of x. Sorry, it's the square root of x plus 0, which is the square root of x. And that is 1 over 2 times the square root of x. 1 over 2 times the square root of x. Beautiful problem there. Wonderful mathematics necessary. Multiplying by the conjugate, we foiled it out. Really, really good math involved. That's why I like to put that one on the test. So again, one of these two definitely would be on the test. If not both of them, you've got to be able to handle when it's a fraction, which is where you get a common denominator first, and then you have to keep, change, flip, and simplify. And one of them could be a radical, where you're going to multiply by the conjugate. Two different techniques, make sure you know them. And then the last thing just says here, differentiability implies continuity. So if you know you can find a derivative, then you know that it has to be continuous at that point. So if it's differentiable, it is continuous. It doesn't necessarily go the other direction though. If it's continuous, does not necessarily mean it's differentiable. So differentiability means continuity. Continuity doesn't necessarily mean differentiability. Hope that helps.